look at a totally new topic, Chapter 4. And there are two sections in Chapter 4. The first section is pretty quick, which is 4.1. And the one that we'll be spending the majority of time on is the second section, 4.2. So let's get started. Probability is something that you may well have experienced in different ways. Probability is connected with terms like chance, and we use it sometimes in our language. If someone went and said, the chance that it rains tomorrow is quite high, or the chance that next year we get a great July, things like that, it is quite low, whatever it might be. Those are concepts. When we use the word chance, those are actually concepts that are related to what's called probability. So in the statistics world, we formalize probability by giving it a number. And so the probability of some event A happening is basically a fraction. On the top, it's the number of ways A can happen. And on the bottom, it's the number of possible events. So probability is just roughly the fraction of time that you would expect something to happen. Now, certain things can be quantified. We can put numbers on them. And so we're going to look at probabilities where that can be done. There are two types of ways that you get these numbers. The first one is called empirical, sometimes called experimental. And the second one is theoretical. So let me do an example. Suppose that you take a dice, right? And you roll the dice. And someone says, what's the probability that you roll the dice and you get an even number? Well, you look at a normal dice and you say, well, when I roll a dice, any one of the 6 numbers could happen, right? I could roll and get a 6, but I could have rolled it and a 2 could happen, whatever. And how many of those possibilities are actually even numbers? Well, there's a 2, there's a 4, and there's 6. So the number of ways A can happen, even numbers can happen, is 3. And what's the total number of things that can happen? Well, when you roll a dice, it's 6. So the probability that you can roll a dice and get an even number is simplified down to the fraction, which is a half. So it depends on the homework how they want that answer. Sometimes a half is fine, that's what you type in. But you can also convert a half to 0.5, which is probably better than fractions. And the reason why I say that is, suppose you were looking at 2 different events, and I told you that one of them was 17/37 and the other was 11/24. Wouldn't it be quite hard for you to tell which one was bigger than the other? Because when fractions do not share a common denominator, isn't it quite hard to tell which one's more likely because it's bigger than the other? And just out of curiosity, I'm going to tell you what these guys are because I just made them up. This one here is roughly 0.4595. And this one here, do you think this one's bigger than that or less than that? Before I hit enter and tell you the answer. Would you think 11/24 is bigger than 17/37 or less?
I would say less.
Well, let's see. It is. Now, if you convert things to decimals, isn't it quite easy to see this guy's bigger than this guy? When it was fractions, you get it, it's much more clumsy. So that is a good way. There is a third way that probabilities are written, and that is that they are sometimes written as percentages as well. And that's not that uncommon as the way that most information is conveyed to non-statistics people. So when they go on the news or something, they might say there's a 40% chance of rain tomorrow. What they're saying here is that the probability that it rains tomorrow is 40%, right? That's how you do it. So if I went and said to you, for instance, what's the probability that you get the number 6? So you roll a dice and you get the number 6. Well, that's 1, because there's only 1 6 on a dice out of 6 possibles. And that comes out as 0.17 if you round it off, or 17%. So far, so good? So as long as this is theoretical, because I'm not really physically rolling the dice, I'm saying if I had a dice and I rolled it, this would be the kind of percentages that you would expect. Now, let's look at empirical ones. Empirical probabilities, experimental probabilities, come about by people collecting data and using that data to make a prediction. So how do they know it's going to be a 30% chance of rain tomorrow? You know what I mean? Because tomorrow it rains or it doesn't, right? So it's not like each drop of rain is only 30% water or something. It doesn't mean that, right? It means 30% chance it rains, the rest doesn't. Well, what you do is you collect data. So you might collect it like this. Let's do, let's say, do the Seahawks. What's the probability that the Seahawks win the Super Bowl? Now, it depends on how you're going to collect that data. One of the ways you could collect it is you could just say, okay, then, how many times have the Seahawks won in the past? Well, any Seahawks fans, how many times have they won the Super Bowl?
I believe it's only once.
Correct. Now, the bottom number I'm not so sure, so I'm going to pretend I know, which I don't. Let's suppose that there has been 50 Super Bowl competitions, right? 50 Super Bowl competitions. So based on the data that we've got, we are talking about a 2% chance that they win. That would be an example of an empirical or experimental probability that they win. Now, how realistic is that? Well, the data I've got is not very good. I mean, it's not a large sample size. So maybe you could come up with better ways to collect that data, like how many times you have beaten various teams, and then collect that as a percentage, and maybe that would be a better reflection of it. Try another empirical one. Suppose that a weather forecast guy collects all the data from July's, and he calculated how many times it rained in July last year. And it rained last year, let's pretend, 11 times. Oops, put the probability in the wrong place. So the probability that it rains in July, any given day in July, is 11 out of 31, which is approximately 0.3, but let's find out exactly what it is. It's 0.35, or 35%. So the chance that it rains any given day in July was about 35%. That's another example of empirical probability. Let's do the last one. What's the probability that you get lung cancer? Well, let's in fact make it a little bit more severe. That you die of lung cancer in a year. And we'll assume that this data is for America, although you could use data from the world. But what's the probability that you're going to die from lung cancer in a year? Well, what you need to do is you need to collect how many people die in a typical year in America of lung cancer. And I'm making this up. It's 250,000. Let's say that's the truth. And then you have to divide by how many Americans there are, which I believe is about 306 million. Now, can you see that as a fraction, that is a very impractical fraction to tell anyone? So I'm trying to sell decimals to you. So 250, 123, divided by 306, 000, 000. And the answer I get is a really weird 8.2, I've rounded it off, e to the negative 4. That is not going to work in your homework if that question happened. Does anyone know what the calculator's trying to tell me when it did this? It means it's a really small number, so it had to go into a special kind of notation to try and draw it, write it down. Do you recognize what this might be?
Isn't it just telling us to move the decimal place to the left 4?
Or for the scientists amongst you, isn't it that guy? Which is what you just said is correct. This is tiny. Would you agree that the chances that you die of lung cancer in a year, if my data was valid, is quite small? So that's empirical, right? I just collected data and you divide them. So probabilities, at least the ones we're doing so far, just really need to know two numbers. Who goes in the top, who goes in the bottom? So here's a trick question. I am warning you right off the bat. What's the probability that you roll 2 dice and they add up to 11? Now this is an experiment. This is not an experiment. This is theoretical. So if you take 2 dice and you roll them, what's the probability then that you roll the 2 dice and they add up to a total of 11? So I need to know two things here, don't I? I need to know on the top how many ways can you get a total of 11? And the bottom one is how many things could happen? Right. How many ways can you get a total of 11 when you roll 2 dice?
4?
Well, let me phrase it differently. Give me a combination of 2 dice that adds up to 11. Let's do it that way. 5 and 6. Would you agree? Is there another way of getting 11? And this is where people don't pay attention. They don't, not so much pay attention, but don't realize that there is another way.
6 and 5.
You're right. And the reason for that is that aren't these 2 dice individual objects? So that one being a 5 and this one being a 6 is not the same thing as this being a 6 and that being a 5. If you want to make it even more, can you pretend that one of the dice was red in color and the other was blue? Can you see that those are 2 distinctly different events that add up to 11? So the top number is 11. Now, a much more difficult number is how many things can happen. How many different ways can 2 dice be rolled in total? Oh, and I put 11 there. My apologies. 2. There's 2 ways to get 11.
Well, each dice has a 5 and a 6, so.
No, that's for that. But forget about the total now. The bottom number is, it doesn't care what it is, but how many different things could happen. Right. Okay, how many things could happen on the first dice? Would you agree that the first dice, there's 6 numbers that could happen, right? And how many things can happen on the second dice? Isn't there 6? But for every one of these 6, couldn't there be 6 of them happening? So that makes the bottom 36. Now, if I had time, I would write them all down. But can you imagine a 1-1, a 1-2, a 1-3, a 1-4, 1-5, 1-6, 2-1, 2-2, 2-3, and keep going. 6-1, 6-2, 6-5, 6-6. If I wrote all of those down, can you trust me? There are 36 of them, which means that as a fraction, it's that. And as a decimal, it's about 6%. What total on a dice is the most common total? So you roll 2 dice and you add them up. What's the most common total? I mean, a 12 doesn't happen that often, right? And you don't get a 2 that often. So what kind of number do you think gets you, happens more often than any other total? While you're thinking of it, I'll give you a choice. The most common total when you roll 2 dice, right, the one that's going to happen more often than any of the others, is either a 6 or a total of 7. Which do you think it might be? And you have a 50-50 chance of guessing correct, which is probability as well.
Is it 7?
It is. Was that a guess, or do you have an inkling why it might be 7? But you're right, it is a 7.
7 just because it's bigger, so there's probably more chances of different facts.
There's more ways of getting a 7 because there's more room to get to a 7, something like that.
Yeah.
Okay, that's an interesting way of looking at it. It doesn't make it wrong, it's just a way of looking at it. So let's check them up. We know that the bottom number is 36. Right, if I wanted to get a total of 6, and I wouldn't normally do this, but for this question, I think I should. Let's look at all the ways you could get a 6. First dice could be a 1, second dice could be a 5. Then you could get what, a 2 and a 3, a 3 and a 3, a 4, I'm out you sync here, that's a 4. Right. A 4 and a 2, and finally, what would the last one be? A 5 and a 1. So if you look at all the ways in which you could get a total of 6, do you see how there's 5 of them? Let's look at how many ways to get a 7. Well, you could get a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, and finally a 6 and a 1. Do you see that there's slightly more ways? There's 6 out of the 36. So knowing that kind of information is fundamental to understanding, say, principles of gambling. See, if I was playing a gambling game with someone, and this is kind of how the history of probability started. People would come to mathematicians, statisticians in particular, and say, hey, there's this new game that you roll 2 dice and you get a total, and depends on what the total is, how much money you could win, and if you don't get that total, you lose. I'd like to play that game, but I'd like to get an edge on it. What kind of total is the most likely winning total? Well, you'd say, hey, if you can only pick one total, pick a 7, because you're going to win more often than you're going than any of the others, for example. And what they basically did is they constructed the idea that a probability is a fraction of the time something could happen. And from there, a whole load of math developed. So, quick recap. Probability of an event A happening is the number of ways A could happen divided by the total number of possible events. There are 2 kinds of probabilities: empirical, where you just collect data to get your fraction, and theoretical, where you kind of just look at the situation and do counting. How many ways could this happen divided by the total number of things it could. Any questions about that, or we go? So let's introduce you to a term called the complement of the event. Suppose A represents some event. So P of A is how we would write down the probability of A. And let me tell you that I happen to know that the probability that event A happens is 55% of the time, right? So probability it rains tomorrow is 55% of the time. Right? Probability that I eat some chips tomorrow is 55%, whatever it is. The complement of A is written with a C above it like that.
Wait, excuse me?
Yes.
Sorry, I can't see your notes or your paper, what you're writing. It's
Whoa.
showing our names, so I'm a little lost.
Can you see it now?
Yes, thank you.
Have I been doing this for the last 10 minutes and not one of you has mentioned it?
It was just for the probability of like the total of 6 and the total of 7, not that long.
Okay, so your job is to remind me when I screw up like that, right? Not you personally, but everybody. Okay, so complement of event. Probability of A, 55%. The probability of the complement of A, that's how you read that out loud, is 45%. The complement is another way of saying the opposite event. So let's give you some examples. The probability that rains tomorrow is 10%. The complement of rain tomorrow, you could phrase that different ways. Couldn't you say the probability that it doesn't rain tomorrow? Or couldn't you just say dry? Would you agree dry is the opposite of raining? And what will that probability be? It will be 90%. So if you take any event in the universe and you know its probability, can you always find the complement by subtracting it, in this case, from 100%? Let's check that out. What's the probability that the Seahawks win? Well, they get a bye week. In 2 weeks from now, it's 25%. That's that they win. What's the complement event going to be then? It's not meant to be a trick question. What is the opposite of winning?
Losing.
Losing, right? So the probability that they lose. Now, can you see that I can do that calculation in my head? But if I was wondering what does that look like, it looks like this. So you can write this down as a formula. The probability of an event plus the probability of the complement of that event is always 1. Or if you want to write it as a percent, 100%. We sometimes use that to help us. Well, let me show you how I might use this result. Let's do the 2 dice thing. What's the probability that you get a total of 11 or 12? Well, there are 36 ways for that to happen. How many ways can you get 12 when you roll 2 dice? There's not many. How many ways can you get a total of 12 when you roll 2 dice?
Once.
1. So the answer is that guy, right? So what? Right. 2 ways of that happening, 1 way of that happening, total of 3 ways out of 36. So what's the probability that you don't get an 11 or a 12? Well, there are 2 ways to approach this second question. Couldn't I just find out how many ways to get a total of 2, a total of 5, a total of 8, a total of 9, finally a total of 10, and add the whole damn thing up? Now, I could do it that way. Probably take me about 10 minutes. Or I could recognize that isn't this the complement of that? Is not getting 11 or a 12 the opposite of getting an 11 or 12? Sure. So if this is 3 out of 36, what's this guy going to be?
$33.
Yeah. Now, do you see that if I knew this, it's much easier to calculate this? And even if they only asked me to get this, do you know I would have found that first and did this? Only because it's quicker. Now we're moving on to, so that's the idea of complement, the probability of an opposite event happening. Now look at the range of probability values. What do I mean by that? Right. Here's a number line. The smallest probability you can ever get is 0. If something has a probability of 0, it means it's never going to happen. So the probability that a politician's going to tell the truth all the time is 0. And you can also use percentages, which I kind of like. What's the biggest number the probability of any event can be? What's the maximum value?
1 or 100%.
Yeah. And when you talk about an event that has 100% probability, that means that particular event, it will always happen. So that would be, what's the probability it's going to rain at least one day between now and Christmas? Well, in Washington State, that's pretty close to being 100%, right? And theoretically, at least, it is 100%, right? Everything else is in that range. So if someone does a calculation and they end up with a probability of 1.2, doesn't that mean that you've made a mistake and you better go back and look at what you did? If you get a negative probability, that's impossible as well. Go back and check. Now, if I put in the middle 50%, which has a decimal as 0.5, we might use a term like 50-50? Even? You ever use terms like that? Ah, it's a 50-50 chance it's going to rain tomorrow. Or it's an even chance of raining tomorrow. You familiar with an expression, something like that? Maybe a Britishism, but I don't think it is. Does anybody know, I can't think of any others, but maybe there isn't. But does anybody know any other terms that you might use for a situation where it's just as likely to happen as not? You know, it's kind of balance. I guess there isn't one, at least I can't think of one. Are we good? Right, so there is some questions. I think one of the homework questions goes in and it talks about which ones of these probabilities are not possible or something, and this would how you would figure that out. We're going to now look at a thing called the law of large numbers. So I'm going to introduce you to a term called relative frequency, which we have met before. So basically what you have here is an experiment. Something that you physically do. And from an experiment, you can calculate what are called relative frequencies. So let's suppose in this experiment, I roll a dice. Nah, I've done dice. I throw a coin in the air. That's easy, right? And I throw this coin in the air 100 times. And I want to know what the relative frequency of getting ahead is. Well, the bottom number is 100. And let's just say, for argument's sake, that when I did this, I got 52 heads, which comes out as a very nice number, 0.52. And that is a relative frequency. Also, just for completeness sake, 52%. So that's a relative frequency. Now, what is the probability, theoretical now? Put it over here. What's the probability that you throw a coin in the air and you get a head? Well, there's only two things that can happen, and only one of those is a head, and that comes out as only 50%. That didn't match this number, and nor should it. Probability does not tell you what's guaranteed to happen. It really just tells you the chance that something is about to happen. So let's argue it through this way. Can we imagine that I did 1,000 of these? So that's a really boring job, but I threw this coin in the air, counted how many times a head happens, and I'm going to get the relative frequency of getting a head again. Now I know that the bottom number is 1,000. Should that top number be 500? In other words, every time I throw 1,000 coins in the air, should I get exactly 500 heads and exactly 500 tails? Is that the way the world works? What do you think?
Theoretically, yes. Experimentally, no.
That pretty much covers it. Experimentally, couldn't I get 510 or 498 and any other number roughly close to 500? Probably. But theoretically, right, isn't going to match reality. So I might not get what I wanted. But in realistic terms, right, wouldn't I expect a number darn close to 500? For instance, if I threw a real coin in the air and I didn't do any tricks, I wasn't, trying to make things happen, I just randomly threw it in the air, wouldn't I expect round about 500, give or take, a relatively small amount? Suppose somebody said they threw the coin 1,000 times and every single one of those was a head. Yeah, I would think they're lying. Would you agree? That is just not likely. What the law of large numbers tells us, it doesn't tell us that the relative frequency at any given size is going to be exactly 50%. But what it does say is that the more and more you do something, the closer this number will get to 50%. So if you threw a coin 1,000,000 times, you won't get exactly 500,000, but that fraction becomes smaller and smaller, or at least comes closer and closer to 0.5. So can you imagine here, it was the number of times I threw the coin, and here I matched against it the relative frequency. And here is the magic 0.5. Well, I might get a number that's up here, and then a down here, and then here, and then here, and then here, and here, 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 here. What you get is a kind of wavy line that's never quite going to be in 0.5, but isn't it going to be darn close to it, especially when you do it thousands upon thousands of times. And that's what the law of large numbers tells us. It tells it as n, which is the number of trials. And that's just jargon for how many times you do something. Gets larger. The relative frequency gets closer to the probability. So if we have collected hundreds of years of weather data and we use that to predict the probability that it's going to rain, we start getting really close to reality. It doesn't mean that we get it right all the time, but at least we can put a pretty strong degree of confidence that what this number up here tells us is going to be darn close to what would have happened. So give me a little story to show you what's going on here. Somebody was playing a game where they were looking at throwing the coin and getting ahead. Right? We've already said that the probability of that is 50%. That's what theory says, right? So he tested it out, and this guy did it 100 times, and he got to the 99th throw, and at the 99th throw, he found out he had 49 heads and 50 tails. So throw number 100 is going to be done, right? About to throw the coin in the air. And his false logic is this. I know that the answer should be 0.5 theoretically. And so doesn't that make the head more likely to happen so that what I expect to happen is 0.5? You get the kind of argument that he's thinking there. What is the chance that the next coin is going to be a head?
50-50.
Still 50-50. The coin does not know that it's been thrown in the air 100 times, right? The coin doesn't know that it's went 49-50. For that to be true, shouldn't the coin have a memory and it should be saying to itself, hey, this guy's going to want me to go another head here to get this balanced. I'm going to have to move myself in there. You know, it almost implies that the coin has a will or a brain or a thought process, which is totally silly. So the idea that probability tells you what's guaranteed to happen is false. What probability does instead is it gives you a number that tells you in the big picture how likely something is that's about to happen but hasn't happened yet is going to take place. Show you another story that is caught out by gamblers. Called the Monte Carlo fallacy. Monte Carlo fallacy. This is how it works. You imagine a roulette table, big circle thing. And one of the bets you can do in roulette is red or black. Right? You can bet a red number's going to happen, and if it does, you win money. You can bet a black number's going to appear. If you've ever watched movies, you probably know what I'm talking about. Right? And the Monte Carlo fallacy goes like this. Imagine you were there in the casino, and 70 times in a row, it was a black number. Not the same black number, different black numbers, right? But 70 times in a row, it was black. Right? And you've just been watching this. You haven't been gambling. You've just been watching. And now you think, it's my chance to win big. So you take your life savings and you go like this. Blacks are happening a lot. I'm going to bet all my money on black. That's one version of the Monte Carlo. It thinks that there's a run of black numbers. Somehow or other, the machine is just generating, you know, stop on black numbers. And you bet all your money on black. Second one goes like this. Do you know, these things are meant to average out, right? You're meant to just get as many black numbers turning up as red. I'm sure that a red number is definitely due. It's time for me to bet my life savings on a red number. Both of those are fallacies. Both of those are just wrong. Isn't the chance that the next number that, you know, ends up on a roulette table is black or red, if we cut out the greens, isn't it 50-50 again? Every single time, it's the same chance. Previous events have no effect on the future. We cool with that? So don't go to Monte Carlo and bet all your money because that happens. Because you will have a 50-50 chance of losing it all. Now we're going to look at a thing called sample space. Sample space is, oops, I guess I'll call it a list of all possible outcomes. So a sample space for an event is a list of all the possible things that could happen. So let's do a story for that. Let's look at 3 children families. The sample space. Well, we have to write down all the things that could possibly happen in a 3 children family situation. How many things do you think there are here? How many different ways can you get 3 children families? I mean, boy, boy, boy is one example, right? Boy, girl, boy is another. How many different ways could 3 children families have? Any takers on that bit? First child in the family, second child in the family, third child in the family. This is a counting technique. Would you agree that the first child could be a boy or girl? So that's two choices. So could the second child be a boy or a girl, and so could the third child. That tells me that there are 8 possible things that could happen. So let's try and write them down and create this sample space. Well, you could go 3 boys. And that's it. There's only one way of getting 3 boys, right? Everybody's a boy. Now, let's look at getting 2 boys and a girl and how that could happen. Well, couldn't the girl be the first one in the family? Couldn't the girl be the second child in that family? Or could the girl be the youngest in the family? And isn't that the 3 ways in which you could have 2 boys and a girl? 3 different combinations. Now, the next combination would be a boy and 2 girls. So you could have a boy at the front. The boy could be the second child. Or the boy could be the last child. Now, right now, I've written down 7 different things, haven't I? What's the last one? Because we know there should be 8 because of this calculation. Who's missing from this family combination?
3 girls.
Girl, girl, girl.
Agree, 3 girls or girl, girl, girl. There's your sample space. Sometimes you need to create this because there's going to be probabilities that you're going to be asked to find that are quite difficult otherwise. So let's suppose I say to you, what's the probability that you get 2 boys and a girl? And I don't care what order they're in, right? It's just 2 boys and a girl. Well, I know that the total number, because we've already done that, is 8. And don't you just scroll through these and you count 2 boys and a girl? How about that top one? That one under it and that one under it. Do you see the answer is 3 8s? Suppose I said to you, what's the probability that you have a girl as the first one and a boy as the last one? So the girl has to be first and the boy has to be last, but the middle one could be anything you like, right? So we need to go through this 8 and we have to figure out who this represents. Well, if I put a little marker on it, would you agree that this one suits that? Is there anybody else in that list who also suits this particular situation?
Girl, girl, boy.
And so the answer to this one is what? The quarter. Now, if you didn't have that sample space, could you imagine how much more difficult it would be to find the top and well, definitely the top number, right? Whereas if you've got this, you can look at it and you can count it any way you wish. What's about a little table that looks like this then, which is called a probability distribution table? And what you do here is you do number of boys in the family and then the probability of that happening. So in a 3-child family, you might have no boys, 1 boy, 2 boys, and finally 3 boys, right? If you do 0 boys, isn't that just 3 girls then? So that's 1 out of 8. If you do 1 boy, that happens 3 out of 8. If you do 2 boys, that also works 3 out of 8. And the chance that you get all 3 boys is 1 over 8. That's called a probability distribution, where you look at, in this case, counting the number of boys, and you figure out the probability of every single one of them happening. What do you think these 4 probabilities must add up to if I do it correctly? What number must they add up to?
1.
Correct. So if you ever get a probability distribution question and you want to do a kind of quick check because it's a test question or whatever, shouldn't you add them all up and see if it comes to 1? So if it's decimals, they add up to 1. If it's percentages, I guess it should add up to 100%, which is what 1 is, right? And if it's fractions, it'll add up. Are we good with that? Any questions? Sample space then is all the different ways something could happen. Let's look at some homework questions so we get a feel for what they look like. I can never find things when I want to. Here we go, click on it. There we go. Right, so hopefully you're looking at 4.1 homework. Can you read that or shall I make it bigger? Anybody want it to be bigger?
It's fine.
It's fine, okay. So question 1 says, suppose that a newspaper states that the probability it rains today is 25%. What is the complement of rain today? And there's 4 choices. Which one would you phrase?
No rain today?
Sounds probably. Now, what's the probability?
0.75.
Right, now, it's a bit annoying and I'm not quite sure what the heck they're meaning because 0.75 makes perfect sense because answer to 2 decimal places. But really isn't that also, whoops, can I do percentages in this? No, it won't allow me to do percentages, darn it, okay. Then I guess I'm stuck with 0.75, but I was going to write 75% and I think what it does, now I remember, is outside the box there's a little percentage symbol when they want percentages. Okay, what's the probability of an event that's certain to occur?
1.
Yeah. Let's get these ones out of the way. And ain't going to happen is 0. That was easy. I'll let you worry about 3 yourself. Right. Oops, we can't have that. That's just going to distract me as well. That's better, okay. So question 4 says a recent survey of 1,070 adults selected at random showed that 649 thought that firefighters had a great prestige. Well, if you want to estimate what that is, won't you take, well, I won't actually do it. Won't you take 649 and divide it by that guy, but round off your answer to 2 decimal places, which is what the nearest 100 does. So it's probably about 0.6 something. Consider a family. We did the family 3 children, right? This one's bigger. Consider a family of 4 children. Right? Assume that the probability of a boy and a girl are the same and that they are independent. List the equally likely events from the gender of 4 children from oldest to youngest. And they go through and they give you all sorts of combinations. And you can pick more than one. So 2 females, 3 females, all males, and tick them. Now, what's the probability? Oh, let's rewind this question. and do it as a calculation. So you got 4 children. Child number 1, child number 2, child number 3, child number 4. Could be a boy or a girl, could be a boy or a girl, could be a boy or a girl, could be a boy or a girl. Do you see where I'm getting the bottom number from? Agreed? Now, suppose I wanted to find what's the probability that all 4 of them are boys. If you had the sample space in front of you, you could just count it, but you could imagine this one, I think. Isn't there only one way that that's going to happen? So there's your probability as a fraction. Turning that into a decimal, we're looking at about 0.0625. And if they said to the nearest 100, that would be your answer. This one is a bit of a challenge, but one boy and 3 girls. How many ways could you get 1 boy and 3 girls? Don't see any volunteers. Oh, good. Someone showed me. It's 4. Couldn't the boy be first, 3 girls, the boy be second, 3 girls, third, 3 girls, 4? Which means about 25%. So if you know anybody who in your family or your next door neighbour who's exactly 4 children, there's a 25% chance, right, a 1 in 4 chance, that that particular family has 1 boy and 3 girls in it. Does anybody know a family of 4? I guess we can't put this to the test, but are we good? Right. Let's return to.
In our homework, if we're reducing do we reduce the fraction of its asking for, or do we always just give?
If they want a fraction, you should reduce it. So don't leave it as 4/8, call it a half, right? If they ask for a fraction. It seems right now that they're more interested in decimals, so let's work on the assumption that answers are decimals unless they say otherwise. Okay, this is homework question 7. Okay, explain why negative 0.41 can't be a probability. And you get 3 choices to explain it. Why can't negative 0.41 be a probability?
Between 0 and 1.
Yeah. Didn't we do that earlier on today when we said, look, 0, it ain't going to happen. 1, it's guaranteed. So you can't get any harder than it ain't going to happen, right? So that's why 0 is as low as it goes. And you can't get any better. And there's some others in there, but I'll let you figure those out. Now, in the next one, you're going to take the information that's here and convert it into here. So let's see. Isabel Briggs Myers was a pioneer in the study of personality types. Okay. The personality types are broadly defined according to 4 main preferences. Do married couples choose similar or different personality types in their mates? And the following data gives an indication. So 28 couples essentially shared no personality traits. Right. So if you were an optimist, he's a pessimist, right? If you like taking risks, he likes playing safe, right? That kind of whatever the traits happen to be. Now that would be 28 divided by the total number, which is 375. Now, if you'd been asked to do it as a fraction, I guess that's the way it should look out. But let's see what it looks like as a decimal. Rounded off to 2 decimal places, 0.07. So 7% of married couples don't have anything in common, at least according to these personality trait tests. So not many people, relatively speaking.
You can't even like take notes on this. Like you just have to listen.
We good?
Yeah, sorry.
Right. So what I was saying here is that, what was I saying? Yeah. So about 7% of married couples share nothing in common. At the other extreme, where they're kind of like twins, personality-wise at least, it's about 9%. And it looks like, well, one of these numbers here is the most likely. Let me pick 2 personality traits. 119 divided by 375, about 32% of couples. So from what I can see, and I'm just making my own kind of judgment call on this, most people get married to someone who share some similarities in personality, but aren't extreme. In other words, they don't have exactly the same as me or nothing like me. They kind of, a kind of balance of we share some things and we don't share others. That seems pretty realistic. I mean, you may know some couples who you wonder how on earth they ever got married or how on earth they ever stayed married, but they're all very happy and it works for them. So they would be maybe one of these exceptions. But we are all uniquely different. So I don't know if I would use that as a way of choosing who my partner is. Like, oh, I don't think I can marry her or him because we share so few personality traits. I wouldn't use that at all. I think that would be a bad way of picking a partner. And it talks about the sample space. In this question, when you look at the way that the data is given, don't they just abbreviate it into numbers 0 to 4? And so that would be your sample space. Dice one we can skip by. Okay, this one's is interesting. This is empirical, right? It came from experimental data, so it's relative frequency, I'm assuming. When do creative people get their best ideas? Right. So, you know, the guy who thought about whatever it is, microwaves. When did he have that thought about a microwave? Well, here is a list of different people and when they made their idea. So they talked to a lot of inventors and said, the last clever idea you had, when did it first come to you? And this bunch of people here, oops, said somewhere between 6 a.m. and noon, 290 of them had it. There are 966 inventors. Let's just pick the biggest number. 302 people had their best idea from 6 p.m. and midnight. So that's 302 divided by 966 into 3 decimal places, that comes out to be 0.313. So over 30% of inventors said that they got their best ideas from 6 p.m. till midnight. Now, if you are an inventor and you work for a company, don't you probably, well, not today because of COVID, but in the past, wouldn't you be working in an office 9 to 5 in the research lab, having the weekends off, just doing a 9 to 5 job? But it looks like they got their ideas after they left work. Would you agree that if you look at these two numbers in particular, isn't that after work is finished? So if you were really in charge of a research and development and you were looking for good ideas, wouldn't you probably tell the guys, don't bother coming into work today, stay at home, and sometime tonight when you have a good idea, tell me about it? Counterintuitive, but that's what it says. Let's see, we got a couple. Yeah, we get 2 more of these to do. I guess I should pick one, but not both. Right, let's do question 12. John runs a computer software store. Yesterday was bored. He counted 137 people walk by his shop. So I'll write that number down so I can keep track of it. 137. 54 of those people came into the store. Of the 54 that came in, 21 of them bought something. But he's going to go out of business soon if that's what he got. So we've got 3 different numbers. And now we're being asked to use that data, and we're going to round it off to 2 decimal places, to estimate the probability that a person who walks by the store will enter the store. Now, since we're talking about people who walk by the store, that will be 137 on the bottom. And how many of them came into the store? And the answer to that would be 54. So 54 divided by 137 is about 39% roughly. Estimate the probability that a person who walks into the store will buy something. Well, isn't that going to be 54 on the bottom and 21 on the top? Because 21 people out of the 54 who made it into the store. And let's see what that number looks like. And that's about 39%, which is really unusual. Estimate the probability that a person who walks by the store will come in and buy something. 137, 21 of them bought something. You see, in this case, the number on the bottom has changed. And that's a lot smaller. It's about 15%. And estimate the probability that the person who comes into the store will buy nothing. I can use one of the answers I've already got to do the last one. Can't I use the fact that I know the probability that they did buy something? And it's this guy. So won't the ones be the complement? Okay, let's suppose you're into business and you want to analyze your company's got lots of stores, right? Your company's got tons of stores, right? Different size. when I look at these two numbers in particular, it's telling me that since these are almost the same percentages, wouldn't it be useful if you had your store in a place where lots and lots of people walked by? Because if 39% come in, right, then you're going to sell more stuff. Would you agree that if you had the store that was up a back street that wasn't a through road, wouldn't it be very hard to get passed by customers? So where are you going to put your store? Well, the prime real estate isn't it on main thoroughfares, right, where people drive by or walk by. So that's the reason for that. Now, the second number just happens to be the same percentage, but it doesn't need to be. Can we pretend that this number here was 0.11? So people come into the store, but only 10 or 11% ever buy something. What does that tell you is going on in that particular store? Lots of people come in, but only 10% buy something. What do you think's wrong with the store?
Too expensive.
Yeah, that's probably one of them. Or the stuff's not that interesting. Just lost my TV screen for a second, so if you bear with me. Yeah. I think I might be getting power fluctuations, and that's not good. Right. So you can imagine, oh, that's the third time my screens are gone. This is weird. Right, so you can imagine in a situation where we're doing, can you still see me? Right, that's weird. My screens are moving around as well, so there's a bit of a wind going on. So if I was in that situation, I'd be looking at them saying, look, we need to fix something or else we'll just go out of business. So we've got to figure out why we can get lots of people coming in, but nobody wants to buy anything, relatively speaking. So that is that section covered. And I'm going to just do an intro to the second section, and then we'll call it quits for today. Probably before my computer dies on me as well. We're going to look at a thing called probability rules. So since I'm doing the intro, I want to get some of the jargon out the way first. Two events are said to be independent if the probability of one happening has no effect on the other. So two events are said to be independent if the probability of one event has no effect on the other. When this is the case, then the probability that A and B happen is simply just the probability of A multiplied by the probability of B. So we're now looking not at one event, but two distinctly different events, event A and event B. So, an example. What's the probability that you throw a coin and you get a head, and you roll a dice and you get a 6? Would you agree that throwing a coin, no matter what happens after you throw it, do you think that has any effect on the outcome of rolling the dice? Would you agree that those two things have nothing to do with each other, right? One doesn't affect the other. So in this case, the probability of a head gets multiplied by the probability of getting a 6. A head happens 1 out of 2 times, and a single dice roll, 1 out of 6. The answer 1/12, which I can now round off, is 0.083. 0.083. There we go. Conditional probabilities. If one event, affects the other, we say that they are dependent. And probabilities will change. This is a bit harder to show you. So going to have to start off with a deck of cards to do this one. Now, if you play a lot with a deck of cards, this isn't a big issue, but not everybody does. So I'm going to have to kind of give you a very quick breakdown of what happens or what you get in a deck of cards. We're talking about 52 cards. So there are 52 cards. And they are hearts, clubs, diamonds, spades. And these are called the 4 suits. And you have an ace, a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you finish with a jack, queen, or king. And each has the same 13 cards. So there are 13 cards that are hearts, there are 13 cards that are spades. The 13 cards are ace. Why did I put one there? My apologies. Ace, 2, 3, all the way up to king. So let's show you a conditional probability with cards. What's the probability that you take a card, right? And the card you get is the King of Hearts. So let's look at that. What's the probability that from a deck of cards, you turn the top one over and it gone, would you look at that? It's the King of Hearts. Well, isn't there only one King of Hearts out of a total of 52? So that would be a very small probability. It's about 0.02. Now, this is how you write conditional probabilities. What's the probability that it's a King of Hearts given that the card is a heart? Now, that guy there is the word given. Now, the world has changed. What's the probability you get a King of Hearts given that the card, so the second event has already happened, right? And it's a king, it's a heart. Well, there are 13 hearts in the deck, and isn't only one of them the King of Hearts? So now the probability has changed, and it has grown to 0.08. These are called conditional probabilities. The probability of something happening given that you're told this event. And this event we can assume has already happened. Let's switch the order. What's the probability that the card was a heart given the king of hearts is already harmed? This is a silly one. If the king of hearts is already harmed, right, isn't there only one king of hearts? What's the chances that it's a heart then? I don't actually need to do that calculation. Isn't it easy just to say, look, if I know that it's a king of heart, what's the chances that my card's a heart? You say, duh, it's a heart. It's guaranteed, right? King of heart is a heart. It happened. The process behind conditional probabilities is quite important because what that does is allows us to adapt probabilities when someone gives us some extra information. So try this one. What's the probability that you get a king, right, given that the card was a heart? Now, it's not a king of hearts this time, just a king. Now, if I tell you that it's a heart, there's 13, and would you agree there's only one king of hearts? Now, let's look at what's the probability of getting a king with no conditions. How many kings are there in a deck of cards? In a normal pack of cards, how many kings are there? 4, right? Wait a minute. Aren't those the same answer? That means getting a king and getting a heart has no effect. Technically, they're independent. Interesting. If you were playing cards and you were a gambler, do you know that your odds of getting a certain card changes as